homogeneous dielectric field fills a parallel plate capacitor. Surface area of 50 centimeters squared. And thickness of 1 centimeter. You are given epsilon relative equals 3 times 1 plus c.
What?
1 plus c.
1 plus c?
Yes.
And is this in centimeters?
Yes. Z is in centimeters.
Okay.
Find the capacitance.
All right. Now, this is one of those problems. First of all, the relative, the separation distance is small versus the actual area of the plates, square root of that. Normally what you do is take this dimension or this dimension, whichever is shorter, and you look at that relative to this, and you can find out that, in fact, if you take the square root of 50, it's like the square root of 49 is 7, roughly. So this is about 7 times as long as that, and roughly they like to be closer to 10, but this is acceptable. We can assume, for all intents and purposes, that the electric field is only going to have a vertical component between them. So the way I would suggest doing that, this problem, and you can do it any way you want, I would assume a charge Q on the lower plate, plus Q, and a minus Q on the upper plate. Now the reason I do that is because you can either assume voltage or you can assume current. Voltage or charge, one of the two. And I choose to do charge for this one because I know beforehand I can get the D field. The D field is not a function of epsilon. Then I can get E field, which is a function of epsilon. Then I can get the voltage by integrating the E field. And it's a pretty easy thing. The other way to do it with the del squared equation requires that I have a it's a del operator on minus the gradient of V is equal to well, I'll put it to you this way. If you do it with the voltage, here's the problem. I know that divergence of E is equal to rho V over epsilon, correct? Now that's Gauss's point form of Gauss's law. Now, if I take E, let me do one other thing. Yeah, is equal to minus the gradient of voltage. Then I get divergence of minus the gradient of V equals rho V over epsilon. And that's going to be del squared of V is equal to minus rho V over epsilon. Now I have a differential equation to solve, but now epsilon, this isn't a constant. Now epsilon is going to be a function of position, and the differential equation can get more problematic, because this is going to be a second derivative with respect to the z direction, and you're going to have two integrations. That said, I choose to assume charge. Is that all right with everybody? Now, I don't know how you did or how the book did it. Once I assume Q, the next thing I'm going to get is rho S, which is simply Q over the area. Does everybody agree with that? Right. If we assume it's uniformly distributed, so that's the charge density. Now remember, these are two parallel plates, and you assume the lower is conducting, the upper is conducting, correct, class? The minute you have that, you know that the E field from here, or excuse me, D field is simply equal to rho S on, that's true, D normal on a perfect conductor. Do you agree with me? You remember we did this? The D field on a perfect conductor is just the charge density. So now I have the charge density D normal, or really D, is going to be equal to rho S, which is simply Q over A. It would be in the AZ direction. The units would be coulombs per meter squared. Y'all agree with what I'm doing here? I'm assuming charge, get charge density. After that, I got D normal. That's the key to this problem, getting the D field. Now, once I have the D field, and this is D normal in this direction, right? Y'all remember this when we talked about this before? Once I have that, now I have the E field, don't I? What's the E field in terms of the D field? Anyone?
Epsilon.
D divided by epsilon, isn't it? So now I take this, which is Q over A, and I divide it by epsilon here, which is going to be 3 times 1, is it 1 plus Z? I'm going to do something, all right? Z is in centimeters. I don't like working in centimeters, this is me personally, because you're going to start with these unit conversions. Epsilon naught is in farads per meter. We would have to convert epsilon naught to farads per centimeter. Do you follow me? This is just me. So what do I need to do with that z if this is measured in centimeters to make it meters? Multiply by 10 to the minus 2, correct, class? So I'm just gonna, this is me, you don't have to do it this way. 10 to the minus 2. So now z's in meters, the measurement, correct? Now after that, that's the E field. Now what do I do? To get the voltage, I do what? If you have the E field, how do you get the voltage? Always integrate, right? Integrate between the lower plate. You can put minus the integral between between the lower plate, which is 0, and the height, which is, I'll just call it D, and that's Q over A divided by 3 times 1 plus Z to the minus 2, and then it would be DZ, right? And this is actually, I'm being a little sloppy here, there would be an AZ, and technically this would be DZ, AZ, and it would be dotted with AZ, but AZ dot AZ is 1. Do you all see what I'm saying here, class? I kind of get casual with that. I know it's going away, so I don't even put it down. Now at this point, oh, sorry, this is Z times 10 to the minus 2. Now, you know, you choose how you want to do this, but I like to just, I'm going to make a suggestion. When I see this right here, Josh, how would you do it? Would you make a variable u equal to 1 plus z times 10 to the minus 2, and then du equal to simply 10 to the minus 2 dz? Would that be okay? I'm just
I
asking.
mean, it's okay with me, but I was just gonna, that just integrates to a log, doesn't it?
It's sure, but the reason I'm doing this is because this constant right here can be problematic. That comes out in front, right?
Yeah, okay.
That's the reason I did it this way. So this becomes minus the integral from 0 to d. It's actually, you can forget the minus sign in this one because it's going to be a magnitude. And then it's going to be q over a. And then I have 3 down here. And then I have u is 1 over plus z to the minus 2, so it's 1 over u. And then I have dz is equal to 10 to the 10, it's 100 du. So this is going to be 100 du. Do y'all agree with that? I'm just putting in a there, correct? What happens then? This becomes q over a, right? 100 divided by 3, and I forgot epsilon naught in here, but there should be an epsilon naught, right? Epsilon naught. And then we get the natural log. And since u is 1 plus z times 10 to the minus 2, when I put in d here for z, I get the upper part is 1 plus d over 100 over, and then it's going to be over 1, right? Correct, class? I mean, it's 8 o'clock, a little after 8. I had a long weekend, had a lot to do with this announcement Friday night, so I've been fairly busy, but do you all see what I've done here? Is that the answer he has? By the way, do you need that 1 in there?
No.
Nah. Does he have that? I don't know if he does. Oh, he's got the number, right?
Yeah.
Or can you put in D is, if that's 1 centimeter, right? 1 centimeter, oh my gosh, that's small. Check it out. Is that what it is?
We need the capacitance.
Well, that's the voltage. Oh, all right. If you want the capacitance, what do we do? If this is voltage, to get capacitance, what do we have to do?
Q divided by V.
It's going to be this divided into Q, correct? So if that comes, then I get the capacitance is equal to Q over V, and that's going to be A times, it's going to be 3 epsilon naught A divided by 100 times the log of 1 plus 10 to the minus 2 over 100 is 10 to, did you do that right? Yeah, I think that's right. 10 to the minus 4. Is that what he has for his answer? have that, Josh? Oh, A, I gotta put in, A is, and that's in meters squared, so it's 50 centimeters squared, which would be times 10 to the minus 4, so it's 50 times 10 to the minus 4, and that should be right, but I don't know. That's 100. Anybody help me on this one? Is that what he has or not? Is that what he has?
3.76. Yeah, but he plugged in, and got the final answer.
I mean, can somebody tell me what that comes to? Because I don't know.
It comes to 19 picofarads.
Can anybody confirm that? I can't do this part in my head. I got 3 epsilon naught, 3 times 8.854 times 10 to the minus 12 times 50 times 10 to the minus 4 divided by 100 times the natural log. And that's going to be about, if I look at that, it's minus 4 times log of, what is it, log of, I don't know. What does it come out to be? I'm taking absolute value here. Just the, is that how you did it, Josh?
No. This, I think that's coming out to 13 picofarads.
That's,
Oh yeah, I'm not getting 19.
what?
I'm not getting 19 on that.
Does he, what is he?
On the bottom, he has just log of 2. Like everything's the same, except he has log of 2 on the bottom instead of 100 log of 1 plus 10 to the minus 4.
All right, now, bear with me here.
Like, I think he just does the whole thing in centimeters and then converts it to.
Yeah, but they should be identical, right? I mean, it doesn't matter what units you, but just work with me here. This is, what is this is epsilon relative, right? He doesn't have a unit here. It's unitless, is it?
Yeah, it's unitless.
He just has this, right?
Hmm?
And if Z is in centimeters, think about this. To put it in terms of meters, right, you would have to multiply by 10 to the minus 2 or divide by 100, right? It would be 100 centimeters would be 1 meter, right? But if that's in centimeters, wait a second. Oh, I see the problem.
1/3 natural root of 2. Oh, it's because Z is from 0 to 1.
Yeah, because it's centimeters, but look, just listen to me for a second. Here's what the error is. If you take a look at here, the value of epsilon relative here is simply 3, right? The value here of epsilon relative should be 6, right? Because Z would be 1 centimeter. If that's measured in centimeters, what I should have done here, since the actual distance is in meters, is multiply that Z by 100. That's my mistake, all right? If you think about that, if we are going to be measuring in meters, just listen to me, then what would be 1 centimeter here, right, would only be 1/100th of a meter, correct?
Mm-hmm.
So you would be multiplying by 100. That was my mistake on this. Did you follow me on this? So this should be, here's the mistake, this should be 100 right here. And this should be, or 10 to the second, this should be 100 times 100. And this should be 100 right here. And this should be 100. And then, if I did that, right here, this would be Q over A. and du would be 100 dz. Yeah, that would be right, 100 du, pardon me. No, wait a second, dz would be du over 100, pardon me, du over 100. And it would be over 100. And then you would have this. And so and this would be log of 2. That's, I believe, what he has, doesn't he?
There's a 3 at the top.
Sorry, the 100 goes away, not the 3. So it'd be a 3 there.
Mm-hmm.
And then, yeah, because there's a 3. That should do it. My bad. I'm sorry about that. That's an easy mistake to make. I don't like working in centimeters. But by the same token, you can see how if z is measured in centimeters, then if you're putting in a value in meters, it would be 100 centimeters is 1 meter. That was my mistake. Okay? That's how you do it. Another one? That was a good problem, by the way. Here's the thing on this one that'll drive you crazy. Not just the centimeter conversion, but you're so used to just going for, well, I guess that you are used to going for assuming a charge. That is the more popular way to do capacitance problems. Assume a charge, then get D, then get E, then get V, and then finally get C. It's always assuming charge. Usually, this is the one exception where a lot of people assume the voltage first, but that can get you in trouble in this one because you got a couple of differential equations, a couple of integrations if you do that, I think. All right. Another one, Josh, or anybody?
Can you do 3, 6, 8?
Yep. Go ahead.
A 1 meter long carbon pipe of inner diameter 3 centimeters and outer diameter of 5 centimeters is cut in half lengthwise.
So the inner diameter is, call it A. A is what again? 1 centimeter?
3
Oh,
centimeters.
3 centimeters, sorry. 3 centimeters. And what's the outer one, B?
5.
B is 5. All right, so it's the rod and its length is what?
Cut in half.
No, it's length.
Oh, I'm sorry. 1 meter.
All right, so then we cut it in half. So it would look like this. Basically, you're gonna have something like this. Inner radius A, outer radius B. All right, go ahead.
Then determine the resistance between the inner surface and the outer surface
Between here and here.
of one of the half seconds.
Uh-huh. And what's the conductivity?
Three times 10 to the 4th.
3 times 10 to the 4th. All right, this is a relatively easy one, and this is gonna be 1 over ohm meters or Siemens per meter.
Positive 4.
3 times 10 to the 4th? That's a very good conductor. Is that, it doesn't matter right now. Just leave it as sigma because it's a constant. Now here's the deal with this one, really. Oops. We're going to assume we're going to place a current I and uniformly distribute it over that inner part right here. So it's going to be that way. And then I is going to cause a J to flow radially outward in that direction. Just think about a whole cylinder for a second. If there's a conducting surface in that inner radius, and I force a current in there, if you had a whole cylinder, it's going to go out radially and it's going to spread isotropically. It'll be symmetric in the cylindrical direction. all right? It will be independent of theta. Do you all agree with me there? Now, the real thing is this. What is this current? If you think about a whole cylinder for a second, just look down the pipe of a cylinder. If I place a current I here, and I let it come out, then there's a current density radially outward everywhere. And if I put a surface at a given distance rho away, then the amount of current penetrating that surface, I know there's a J here, right? The amount of current penetrating that surface over the length of it will be a constant regardless of the radius. So how do I figure out what J is here? Well, I put a surface, and that's a little messy, but I hope you can appreciate it, at a distance rho. Does that make sense to everybody? This is going to be a surface that's going to be half of a cylinder, but it's going to have it at a radial distance rho. And I know all the current coming from this part here that's reaching the outer conductor has to penetrate that surface normally, right? So that means I know the integral of J dot ds over that surface has to be I. Well, the integral of J dot ds is just the perimeter, which is half the perimeter of a circle, right? So instead of 2 pi rho, it's pi rho, right? You all with me on this one? And it's times the current density at that point, which is just J, and it is in the rho direction, so I'll just put J rho. That means J is I over pi rho A rho. Now that's the current density. If it was flowing and it was a whole cylinder, it would be 2 pi rho. And it's times the length. Did they give a length or not? Is it per meter? Wow, okay. We could put an L down here, but it's irrelevant because it's 1, which is a nice number to use if you ever have to choose a dimension. Choose 1. There's no downside. Now, if I have J, how do I do these problems? We assume I, right? If we want resistance, then we get J. After J, we get E, right? And after E, we get V. And after V, we get R equals V over I. That's the sequence, right? So we have J, we need E. How do we get E? Divide by sigma, right? Isn't that right? Sigma E equals J, so we divide by sigma. So we go ahead and we say that E here will be equal to that I over pi sigma, I'm gonna leave with sigma, rho A rho. Finally, how do we get V? And this one's always positive. Class? Integrate it from A to B, right? Technically, you should put a minus sign there and go from B to A, but I'm gonna omit the minus sign and go from A to B because I know it's gonna be a magnitude. Then it's gonna be the E field, which is I over pi sigma rho, A rho, dot, and then, now normally DL here is what? It's D rho, A rho, then it's gonna be rho, D phi, A phi, and then DZ, AZ. But since this is only gonna be dotted into A rho, I only put the A rho component. So I put D rho, A rho here. Now you can see A rho dot A rho is 1. Then I have I here over pi sigma and the integral of 1 over rho, which is, what is the integral of 1 over rho? Natural log, right? It would be the natural log of the outer radius B over the inner radius A. Since that's the voltage, the resistance is just voltage over current, or it's simply going to be 1 over pi sigma, natural log of B over A, and that's it. And I'll tell you what I do on tests at times. So I'm tipping my hat. I'll make sigma a function of position rho. And that way the integral won't result in the same thing. Does everybody follow me on that? If I make sigma here, not to be a constant, but suppose I put sigma is like rho times 10, or rho times 3. Then it would be a 1 over rho squared integration, right? And that would not be natural log, it would be minus 1 over rho. Do you follow me on this? So those are the things I like doing on tests. Just to change the situation enough so if you know what you're doing, it's clear, and if you don't know what you're doing, it's really clear to me, because this is the point where
I'll just see this answer magically appear with a lot of scratching, and they'll say, oh, I must have made a mistake. No, you didn't make a mistake, you didn't know what to do. So. Are we clear? Is there another one? That's a pretty good problem, to tell you the truth. Anybody? You see any evil problems in there, Josh?
3.7 there.
All right.
It's got a coaxial capacity.
Has it got a variable productivity? I'd like something that's
Yeah, it does.
X. This is the kind of problem I like. I don't know what kind of problems Dr. Gross likes. And I can tell you one thing, Dr. Riggs likes problems that he just dreams up. Like, what could I really do to mess with her mind? My take on Dr. Riggs. He's a great professor, but he always gives he used to, unless he's changed, give very challenging exams. Has anybody ever had him? You're gonna have a chance probably to step into his theater. And that's always fun to listen to stories from Dr. Riggs' students. My problems are very much based on the homework. Modifications, not serious ones, but enough so I can tell if you know what you're doing. He has come out of the balloon. Go ahead.
Coaxial capacitor, inner radius 1 centimeter, outer radius 2 centimeters, length of 1 meter.
Thank God. L is 1. Okay.
And then it has 2 different dielectrics along the z-axis, phi relative for phi between 0 and 180.
Oh, okay. They got half of this has some epsilon relative 1, and the other half some epsilon relative 2.
Yes.
Are they constants here though?
Yes.
Now I'm going to tell you the way that he's going to tell you to do the problem, and then I'm going to show you a shortcut. All right. What he's going to say is, for this kind of a problem, the thing that is a constant is the voltage between the inner and outer portions, between here and here. Follow me? Now, if the voltage is a constant, then I can say that the E field integrated from here to here, or from here to here, has to be the same, give us the same results, right? Not charged, but the voltage is constant, right? So how do you go about allowing that? Well, if you take a look at the del squared equation, we know that del squared of V is equal to 0 between the plates because there's no actual charge. Well, del squared in cylindrical coordinates is 1 over rho d rho of rho times dv d rho. And then there's 2 other derivatives terms, but these are derivatives with respect to phi and with respect to z. Now the D field, my contention is that the electric field and the D field are only radially outward because of the symmetry of the situation. And we're gonna have to assume that it's true too, all right? So both are only radially outward. That means these other 2 derivatives of the Laplacian, y'all know what I'm talking about in the back of the book? The Laplacian operator has 2 other derivative terms, forget it. This is the only one you care about, and that's equal to 0. Now I go about and I say, well, I'll multiply both sides by rho, just means this goes to 0 again, right? And then I integrate both sides, correct? And when I integrate both sides, I would put d rho over here. Now I get rho dv d rho is equal to some constant C1. Agreed? Now I take this and divide by rho. So I have C1 by rho is equal to dv d rho. And then I integrate both sides of that equation with respect to rho. And I get V of rho is equal to C1 times the natural log of rho plus C2. And that is the equation for the voltage between the inner and outer conductor, correct? So if he wants capacitance for this one, this is how he'll tell you to do it. I'm going to put a charge, or I'm going to put a voltage on the inner conductor. Say I put plus V naught here and I ground the outer conductor. Now he may not do it this way, but I think he does it this way generally. He finds the voltage and he gets the capacitance based. He gets the equation from this, then he gets the capacitance. Now, if that is the case right here, I can say, when rho is equal to B, the voltage is 0. So I'd say 0 is equal to C1 times the natural log of B plus C2. That's the first equation, right? That's for the outer. And at the inner radius A, the voltage is V0. So then I put V0, or V0 plus, is equal to C1 times natural log of A plus C2. Correct, class? And now I have two equations with two unknowns, and I can see here that C2 is minus C1 natural log of B, right? So I can say that this V0 plus is equal to C1 natural log of A, and then C2 is minus C1 natural log of B. And I can manipulate that, and I can have it C1 times the natural log of A over B is equal to V0 plus. Do you all agree with me there? And if I have A and B, I can calculate C1, right? Correct, class? And actually for this one, C1 is going to be negative, but that doesn't matter, right? Because the log of that is negative if A is smaller than B. Now, if I have that, so if I have, basically I have C1 is equal to V0 plus times, or divided by the log of A over B here. Then what I can do, if that's the case, then I can get C2 here is just equal to minus C1 log B, right? And that's equal to minus, well, C1 is this, minus V0 plus over log A over B times log B here, right? And I think I got that right? Then we can go and say that V of rho here is equal to C1 minus V0 plus natural log of A over B times the natural log of B times the natural log of rho plus C2, which is V0 plus over natural log of A over B. And if that's V of rho, then I can get the E field, and the E field would be minus the gradient of the voltage, which is minus the derivative of V with respect to rho. Do y'all follow me on that, class? Here's why I'm getting that, because I'm going to get the D field. Now once I have the D field, then D normal is rho S on those two surfaces. Follow me on this? So what's this going to be? Well, when I take a derivative of this with respect to rho, I'm going to get a 1 over rho here times all this. So I get this being equal to minus V0 natural log of B over the log of A over B times 1 over rho. Let me stop for 1 second here. I'm going to simplify this. This actually should be B over A. That was my mistake. And That means here C1 would be equal to V0 plus over natural log of B over A. That's better. So this is just going to be V0 plus right there, and it's going to be times this is actually going to be V0 plus divided by the natural log of B over A, or times the natural log of A over B. Either one's fine. And now, if I have that divided by rho, then this is the one. Now that I have that, I can come over here and I can get the D field. Now D is simply equal to epsilon E, correct? Follow me on this right now. If you just understand, this is based on my assumption of V naught is on the inner conductor and ground the outer. This is going to be the equation for the E field, and it would be in the A rho direction if you want a vector, right? Now once I have the E field, I can get the D field by simply multiplying that by epsilon. So that's going to be equal to, and it depends if you're here or here, correct? So if you're in region 2, then it would be epsilon relative 2 times epsilon naught times the E field, V naught plus, right, times natural log of A over B divided by rho. And would be in the A rho direction. This is in region 2. In region 1, the D field would be equal to, call that D2, D1. It would be equal to epsilon relative 1 times epsilon naught times V naught plus times natural log of A over B, A rho over rho. Now, how do we get the total charge now that we have the D field? Just think about it. We want the total charge magnitude on either what? The inner or outer surface, correct? Well, how do you get it if you have the D field, class? We just did this one. We did this. What is the one thing, the relationship between the D field and charge on the surface of a conductor? Yeah, it's equal to rho s, isn't it? So right here on the outer surface, it's equal to rho s in magnitude, correct? Or on the inner surface. We can go to the outer, right? So on the outer surface, when you look at this, my total charge Q would be equal to the charge density in region 2, which is that, that's epsilon relative 2 times epsilon naught times V naught plus times natural log of A over B, and then it's divided by the outer surface radius divided by B, right? It's going to be that, and then it's going to be times, well, that's the charge density right here. That's D is rho s, correct? Then I have to multiply it by the surface area, which would be the perimeter, right, of that. It's only half of it, so it's not 2 pi B, it's pi B, follow me? Times the length 1. So this is going to be that times pi times B times 1. That's the charge just on region 2. In region 1, it's going to be epsilon relative 1, epsilon naught, V naught plus over B times natural log of A over B, and then it's going to be again by pi times B. And that's the charge, right? And what do you know capacitance is? It's charge divided by voltage, isn't it? So it's, if you divide this by voltage, V naught plus, then you get this. And now I'm going to show you an easy way to do this. But that's the way he wants you to do it. Is that the way he did it in his book?
You just had a formula and plugged it in. Don't know where the formula came from.
All right, well, this is the formal way to do it. We solve the del squared equation. And you see the E field varies only as 1 over rho, because the voltage has to be the same in region 1 and 2 between the inner and outer surface. Now here's the easy way to do this type of problem. First I gotta ask you one thing. Back in the day when you had circuits, you learned some stuff. If I have 2 capacitors in parallel like this, call this C1, C2. What is the net capacitance here? You simply add the values, right? Because the parallel plates effectively, the areas of the plates add and the separation distance remains the same, correct class? Well, what if you had two capacitors in series? What's the capacitance here? C would be equal, technically it's 1 over, C2. 1 over C1, right, plus 1 over C2. It's like resistors in parallel, right? But you can do it just C1, C2 over C1 plus C2. It's like resistors in parallel. You can do that. But my point is this. When you look at this situation and you look at the problem we had, what it really looks like when I have epsilon relative 1, epsilon relative 2, it looks like we have a capacitor here, C2, and a capacitor here, C1, that we could easily get the capacitance of this thing if it was filled completely with either one of those materials, right? So here's my contention. If I have a capacitor with inner radius A, outer radius B, and 1 meter long, and some value epsilon relative here, then the capacitance of this system is simply equal to what? You remember what it was? It's epsilon naught times pi, right? Times, the way we actually did it. Do you remember doing this problem? We can do it real quick if you don't remember. This is one of those formulas you kind of keep in the back of your mind. If you do this problem, and this is a cylinder, usually we assume Q on the inner one, then we get D, right? And D would be equal to Q per unit length, assume Q over 1 meter, this 1 meter long pipe. Then we get D as Q over simply 2 pi rho, A rho. Do you remember this? That would be the D field because it's the total charge. Since we have a 1 meter section, it's just Q over 2 pi rho, A rho. Then to get the E field, what do? Just divide by epsilon. So it'd be epsilon, and I'm going to leave it as epsilon. That's epsilon naught to epsilon r. So then I divide by epsilon, and now I have E. And once I have E, I get V by saying it's the integral of that, the integral of Q over 2 pi epsilon rho, A rho dotted with A rho, D rho. And I go from the inner radius A to the outer radius B, and I find, lo and behold, that's simply Q over 2 pi epsilon naught times natural log of B over A, and that's the voltage. And finally, I get the capacitance by taking Q over V, and the Q's cancel, and I get 2 pi epsilon relative epsilon naught divided by the log of B over A. All right? Now that would be the capacitance, you should know this formula, between the inner and outer conductor per meter of a coax system. You'll notice it's proportional to the log, it's inversely proportional to the log of B over A. And as B over A, what happens when B becomes A? In other words, when the thickness of that capacitance goes to about 0. What's the log of 1?
0.
And 1 over 0 is infinity. Capacitance goes to infinity. Always check that. Whenever you get a formula for final capacitance, think about what happens in the limit when the inner and outer plate are at the same point. And it should go to infinity. If it doesn't, you've made a mistake. Follow me, class? Now, here, that's the capacitance as if the whole thing was filled with that dielectric, right? If only half of if the material's in only half of the dielectric, isn't it reasonable to assume it would only be 1/2 that value? So here's how you do it. You can say the C total for this one would be simply like the capacitance of this system if it was completely filled with epsilon relative 2. So it would be 2 pi epsilon relative 2 epsilon naught over the natural log of B over A. But then it's going to be times the proportional area that it is filled with. It's exactly half the area, isn't it? If you think about this, half of the plate area has one epsilon, and the other half of the plate area has the other. So you multiply by the actual proportion of the total plate area, 1/2. Then it's gonna be plus 2 pi epsilon relative 1 epsilon naught over the natural log of b over a. That would be as if if this would be the amount of capacitance was filled completely with epsilon relative 1. And now we multiply it by the proportion of area that is filled, which is 1/2. And that's the same exact thing we got there because the 1/2s kill the 2 there. And you can see that formula, somehow, I missed the pi. There should be a pi in here. There it is. Oh, there it is. No, there it is. But when you look at this, these are the same exact thing, but this is a lot easier in my opinion. Once you know that that's the capacitance, if it's completely filled, if I have any goofy setup like that, I can get it by a proportionality thing. Let me just do one more to show you. What if instead of this, suppose we had this. We're gonna assume it's 1 meter long. But now I'm gonna say this is epsilon relative 1, and the rest is epsilon relative 2. And I want the capacitance of this system per meter. How would you do it? Inner radius A, same as before. Outer radius B, and it's only 1 meter long. Just think about what I said. What would you do? Go ahead.
Maybe the same thing, just multiplying by 1/4 instead of.
That's exactly it. I take the capacitance formula. Remember that one now. That's going to be equal to, this would be 2 pi, right? And I'm going to be 2 pi epsilon relative 1 epsilon naught over natural log of b over a. That would be if the whole thing's filled with epsilon relative 1, but how much is?
1/4.
Right, 1/4. Then plus 2 pi epsilon relative 2 epsilon naught over the natural log of b over a. Then it would be times what? 3/4. And lo and behold, that's how you would do that problem. Now it's the same exact thought process you do it for a sphere. If I take half a sphere and I make it epsilon relative 1, the other half epsilon relative 2, you would do that. Follow me? But it's the area proportion. It's always the area. Okay? That's a good problem, by the way. Anything else? I'm glad we're taking this time to the problems. Those are all good problems. Anybody? Out of curiosity, well, no, I'll stop there. That's how you do if they were in parallel, right? What if they're in series? How do you do? What if we have this problem? It's a good problem. Think about it. What if we have inner radius A, outer radius, let's do a spherical one, outer radius B, and then another one, C. And this is a sphere. Here's the inner core, it's all metal, and the outer part's metallized, if it's a sphere. How do I get the capacitance of that? Call this epsilon relative 1, epsilon relative 2. Anyway, what does it look like to you? He's looking at me like, I'm not gonna answer this. Make somebody else choke it up. Doesn't it look like two capacitors in series? There's the first, there's the second, right? Isn't that right? Now these are spherical capacitors, right? They're in series. What's the formula for a capacitance of a spherical capacitors? Anybody remember? All right, why don't we do it? All right, it's been a while. Huh? How would you calculate the capacitance of a spherical capacitor? Here's the deal. Inner radius A, outer radius B, right? Epsilon relative in between. I go with the Q formula. So if you assume Q on the inner conductor plus Q, right? What's my next step, people?
Find J.
It's capacitance, not resistance. D. It's my head, it's all right. D, and what's D? It's Q over 4 pi R squared AR, correct, right? Now after D, that would work for resistance. If you assumed I, then you would find J, then you would find E, then V, and you could find, but this is a good, you could do the same thing with resistances, right? Two different conductivities, right? Just think that way, because that's how I make out tests. I need what next after D? Okay, and I get it by That's right. It's one thing I'm good at, dividing by epsilon naught, epsilon relative. Epsilon naught, epsilon relative, right? Now I have E. After I have E, I need voltage V, so I integrate that. And when I do integrate E dot dl, it's really gonna be this, the voltage actually between them, I'll call it V naught, would be equal to the integral of Q over 4 pi epsilon, I'll just leave it as epsilon, R squared AR dot AR dr, because that's DL, from the inner A to the outer B, is gonna be equal to Q over 4 pi epsilon naught, and then it's gonna be 1 over A minus 1 over B, if you want positive. That's actually probably more correct, but this is what the value of V is. Now, once I have V, how do I get C, people?
Divided by Q.
Q over V, right? Q over V, and so I take 1 over that and I get 4 pi, that's epsilon, 4 pi epsilon here divided by 1 over A minus 1 over B. And that's the capacitance of a spherical system between inner and outer radius. This is another one you should know. So couldn't I simply say I have two capacitances in series? Right? And C1 would be this with epsilon replaced as epsilon relative 1 epsilon naught, and C2 would be this. This is supposed to be a 2. C2 would be that only with epsilon replaced as epsilon relative 2 epsilon naught, right? And if they're in series, you add them as 1 over C1 plus 1 over C2, right? Or C1, C2 over C1 plus C2. And that's the way this works. And engineers, they spot those kind of things in a heartbeat. Anything else? Past homeworks. That's a good homework. These are great problems. You got one for me? Duncan? No? Okay. All right. Now, I wanted to work problems, and I'm glad you were forthcoming with some of the better problems I can come up with. So now what we're going to do is we're going to get into chapter 4 with magnetostatics. And I'm going to try to show you the similarities between magnetostatics and electrostatics, because when you see similarities and patterns, usually it triggers your brain to think the same way you did before. So first, let me just bring it back to electrostatics. If I had a chunk of charge dq here, and I was a distance r away, does everybody recall the differential electric field at that point? E here, or in this case dE, right, because it's a differential charge, is equal to the charge dq over 4 pi, right, epsilon r squared AR. Y'all with me on that? Do you remember what the name of that law was? It was what?
Not Coulomb's.
It's Coulomb's law, that's exactly right. And it's based on measurement. All the laws we have are based on physical measurement, and these are mathematical descriptions of what the physical measurements, what formulas really govern them, or the laws. Now, write this down. With differential amount of current, if I have something that's IDL, I is the magnitude of the current, DL is both the length of the actual chunk of current and the direction, so it's a vector. It would be like, 10 to the minus 2 AZ, something like that. When I have this, if I come a distance R away, right, the differential H field, please write this down, the differential H field created there is equal to IDL over 4 pi R squared, but then it's crossed with AR. AR between source, and I'll call this 1, and receiver, so between 1, 2. That's a unit vector, and that AR 1, 2 that I'm showing you there, or AR, that's simply R vector over R magnitude. And remember, R vector originates at the point where the current element is, the differential current, and it terminates where the actual observation of the H field is. Now, if you look at these two laws, you'll notice they both fall off as 1 over R squared, small r here. It's 1 over 4 pi epsilon R squared here. there's no constant here, it's 1 over 4 pi r squared. Then there's IDL here, but there's a cross product. This is no cross product at all. This is the big difference. Now, I want to say one thing about why I chose the E field and the H field, not the D field. If the D field was there, we wouldn't have the epsilon, it would seem more similar. But the D field, the units are coulombs per meter squared for the D field. I wanted something with a unit that would be either a current or a voltage. The units of the E field are volts per meter. The units of the H field are amps per meter. So you can see the similarities. One is amps, the other is volts. I didn't want a meter squared is really what I'm getting at up there. The D field would be in meters squared, so I left that constant. Now, what does this cross product do for us? Well, if you think about that, if you're crossing with a vector, if this angle is 90 degrees, the cross product, it's the sine of the actual angle, right, between the length or the actual currents, the differential current's direction and the radius vector. When it's 90 degrees, it would be the sine of that angle, right? It would be 1. But when that angle goes to 0, it becomes 0, right? And this is the thing about the H field. If you look at the H field magnitude, if you have IDL here, and you come out a distance, hold the distance constant R, and you're going to say the length of this, not hold the distance, you're going to say the length of this vector is proportional to the magnitude of the H field. What you get is this. You're going to get no H field in the direction of the current or below there at all. It's dead. And the H field has a maximum value at a given distance when there's a 90-degree angle between this direction and the radial vector. Follow me? So that's the law, the differential current. Now the next thing we have to do is apply it to calculate the H field for some very common geometries. Follow me on this, class? So we're going to do it. Anybody want to take a guess at the first type of geometry we're going to encounter? Think when we did, after Coulomb's law, do you remember the first thing we calculated the electric field from?
Point charge.
Well, we already have it for point charge, right? Don't we, class? We have the differential length, right? I gave you the differential H, so we have it for a point. IDL would be equivalent to a point charge, right? If you had like 10 to the minus third, AZ would be a differential length of current times a magnitude of the current in the AZ direction. The next thing you do it for is the infinite line charge or the finite line charge. But you assume that you're going to put the line charge on the z-axis. That's what you did if you calculate the E field based on Coulomb's law. Now we're going to calculate the H field, assuming that we have an infinite current on the z-axis. So if we have I here, and this is the z-axis, right here, we do it by coming out a distance rho, making that 90 degrees, and saying that I have a little chunk of current here. I have some I, dz, az. Remember, that has a vector direction. And this is going to be at a height right here, z. I'm assuming this is the origin. And now I come out, and here's my R, right? And this is where my H field will be. So this is my dH. Well, what is dH? First, better yet, what's R? Let's get that right first. Now, I'm going to slow down for a second. I want to make sure you hear me on this. What I'm about to show you is probably a very common mistake. I need R. R is not rho, R is not z. R is this distance. But it's the distance measured from where the current is, the elemental current, to the point of observation, the H field. Well, if you look at this, do you all agree that it's going to be the coordinates of the point of observation minus the coordinates of the point of source point, right? Coordinates of the point of observation are rho equal rho. The coordinates here in the rho direction are 0, so it would be rho, a rho. Agreed? And what about the next one? Forget phi for now because it's on the axis, so you don't need an a phi dimension, it's meaningless. What about here? Coordinates z here is what?
0.
Coordinate Z here is Z, right? So it's minus Z, AZ. Agreed, class? All right, now when I have that, what is the magnitude of R going to be? Square root of rho squared plus Z squared, correct, class? And then what's a unit vector AR12 going to be? Anyone?
R over the magnitude.
Exactly, R vector over R magnitude. That means my DH will be equal to IDL. So I put down IDL, I'll write it again. IDL crossed into AR over 4 pi R squared. So here, it's going to be I DZ AZ crossed into AR, and I'll get to that in a second, over 4 pi, and R squared is just going to be what?
Rho squared plus C squared.
Right, thank you. Now, I need to cross it into AR, and AR is really R vector over R magnitude, so it's going to be crossed into rho A rho minus ZAZ over square root of this, which makes this 3/2 power. You all see what I've done here? Now, I want to stop there, that's DH. And the next part, I want to make sure I'm clear with everyone. Is everybody with me up to here? Guys? All right, now please listen here. Sometimes it used to be hard for me after about 55 minutes or so listening to a lecture. I would sort of get saturated. But does everybody understand what I'm doing up to this point? Now, the cross product becomes critical here. I want you to see what happens. AZ crossed A rho is, do you remember this? It's always the coordinates are what? Rho, phi, Z, right? So Z crossed into rho would be phi. Do you agree with me? Positive A phi. So here, AZ crossed A rho is positive A phi. But what is AZ crossed AZ?
0.
0, remember that. So I just get rid of that term, and then I get rid of that, and I make that A phi. So it's rho A phi. Y'all with me on this? Now, if that's the differential H field, I want the total H field, what's my next step? Integrate from from minus infinity to plus infinity in the Z direction. So now I say H is equal to, I'm going to take out the constants, I over 4 pi. Rho does not vary with this dz integration, so I can even take out rho. And then I have the integral of dz over rho squared plus z squared to the 3/2 power, and it's in the A phi direction, and that goes from minus infinity to infinity. Now this is one of those trig substitution things, and do y'all remember when we did this, same thing for the infinite line charge? We got the sine, remember this? We ended up with the sine of the angles. I'm just going to tell you for the infinite case it comes out to this. We'll do this more formally later for the short ones. It's going to be I times rho over, I over simply 2 pi rho in the A phi direction. And that is the H field from an infinite line of current at a given distance rho away. And rho is always going to be the perpendicular distance to the actual line. And A phi is always going to be, matter of fact, write this down, because people always think that A phi means the phi direction associated with cylindrical coordinates. If this wasn't on the z-axis, suppose it was oriented at y equals -5, but up and down the z-axis, then it would have, A phi would have a different meaning. Even though it's a little tricky, A phi is always in this, for this, when you're using this as the, when you're talking about this relative to the center axis of the line. A phi is always going to be equal to it's always going to be equal to the AI, the direction, unit vector in the direction of the current crossed into AR, a unit vector in the direction of the radial distance measured from the source point to the point of observation. That will always be A phi. Follow me? And it's good to note that too, because some of the problems they'll put a line charge on the x-axis, or they'll put a line charge at rho, say at y equals minus 10, and then you have to get the appropriate value of A phi, an infinite line charge, and that's important. I'm close. Do you have 9/11? Is my watch?
9/12.
Yeah.
Close enough. I got a couple more minutes to mention something. That is for an infinite line charge. For something that's less than infinite, from, say minus d to plus d, or minus d over 2 to plus d over 2, it would be this, but I'll tell you what would happen. You would then you would have h as a function of rho be equal to, and then it would be I over 4 pi rho, and they're going to have sine of the first angle 1 plus sine of the second angle 2, where the angles will be measured this way, theta 1 and then theta 2. Now, when it becomes infinite, this goes to sine of 90, which is going to be 1. This would go to sine of 90, which would become 1. You would have 2 divided into 4, would make it 1 over 2 pi. But that's what that integral will go to. Now that's the infinite line in a nutshell. The next thing can you take a guess at the next configuration of current we're going to look at? Based on what happened with Coulomb's law. Take a guess.
Infinite plane.
We could do that one, but there's one in between. Do you remember the loop? The loop's easier. The ringer charge. So the analog to the ringer charge, we could do that one, but it's easier to do the loop first. All right. Now, if one answer, I was hoping that. All right, when we're out a radius A, now we're going to have a current IDL at a given radius A, and now I want the differential H field up here. That makes sense to everybody? Instead of a chunk of current, I have a chunk of chunk of charge, I have a chunk of current. Here's where it becomes important you take note here. We're assuming this be the z-axis because it's symmetric and it makes sense to exploit symmetry. Don't ever make a problem harder than it needs to be. You'll learn as engineers to make things as simple as possible without making it too simple, without omitting something important. Well, IDL is really going to be I. The differential length is really a differential part of that perimeter, right? So it's always radial distance times d phi. So that's going to be, in my case, A d phi, and the direction given would be in the A phi direction. It's swirling around that thing, right? Around that z-axis. That's IDL. Now I plug this into the formula, and I have dH is equal to IDL, which is going to be I, A right here, d phi, A phi. And IDL crossed into AR. Well, first I got to get R. So what is my vector R here going to be? From the source to the point of observation. We'll use cylindrical coordinates. Anybody? How about the variation of rho? What's the source point? What's the observation point's rho value? 0. Rho value here. So it'd be minus A, right? Right? A rho. So I'll just put down there, R would be minus A rho, and what about Z? Plus Z, right? AZ, exactly. So that means R's magnitude would be equal to square root of A squared plus Z squared. And I have IDL over 4 pi R squared which is gonna be a squared plus z squared, right? Then it's gonna be it's gonna be crossed into AR, which is really gonna be R vector over R magnitude, which is minus A rho plus Z A Z over that, which makes that 3/2. Do we all agree with me there, class? Now I was a few minutes late, so just bear with me. If you look at this for a second, work with me here. I have A phi crossed A rho. Now let me do something. For coordinates in general, we give them, render them as rho, phi, z. And whenever we have this, that's first one's rho, when we cross rho into phi or phi into z or z into rho, those are positive. When you go the other way, those are negative. So if I think about it, it's when I go to A phi cross A rho right here, isn't that minus AZ? Correct, class? That would be minus AZ. And then when I have A phi crossed AZ, what do I get? Plus A rho, correct? Now, do you agree with me then? Now stop for a second. A rho is in the radial direction. I want to make this argument of symmetry. Now, in general, if we looked at this, the differential H field, if this is R, will be perpendicular to this, it'll come out this way. It'll have both a horizontal and a vertical component. Can you all see if I go right straight through the center of that circle, on this side, I would also have an IDL of the same magnitude, it'd be a mirror of it, correct? Only it's going the opposite direction. So if I come up here, I'm gonna find that I get the same exact magnitude for the horizontal component, only the opposite direction. My point being that the radial component will cancel. All right, there will only be a vertical component that survives. And in that case, I can come here and say, since A rho since A phi, right, crossed into A rho is minus AZ, that will become a plus, and I'm left with this. Simply rho AZ here. Wait a second. Minus A, this is A squared, so this would be an A squared, pardon me. I'm using rho equal A, pardon me. Now, at that point here, I have DH, right? And it's a function of d phi. What happens when we integrate this from 0 to 2 pi? It's supposed to be 2 pi up here. Class? Isn't it just multiplying by 2 pi? And can you see that the 2 pi will cancel into the 4 pi, you get 1/2? So you get the total H field, now I'm done. Total H field is going to be equal to IA squared over 2 A squared plus Z squared to the 3/2 power in the A Z direction. And that's it. And I'll tell you one other thing. It's in the book. I'll give you some more homework on that, and we'll talk Wednesday. Thanks for staying with me. Sorry to be late. Have Dr. Gross to have you out. Get out of my class.